This is this is good. Yeah, thanks. That's good. All right. Is this thing on? Maybe, maybe not. Yep. All right. So so we left off yesterday with after discussing the Hawking effect that observers far away from a Schwarzschild black hole formed in gravitational collapse will actually see radiation coming off the black hole with a thermal spectrum. And so we're going to consider a closely related effect now, which is that actually in flat spacetime, in just Minkowski spacetime, if we have an observer who is uniformly accelerated, Unruh argued that they will also see radiation, and that radiation will have a thermal spectrum. Now, I'm going to start with a suggestive formal argument, which is analogous to our Euclidean black hole considerations. And then I will do a sort of a slightly better version. So what we're going to consider is an observer that is uniformly accelerated in some direction. And we're going to call that direction x because we can. And so the interesting discussion is only going to involve this one spatial coordinate x and time. And this is in Minkowski space-time. So let's look at the space-time diagram that I have in mind here. So we have t going up. This, as usual, we have units where c is 1. Here's my x variable, and I'm going to think about a uniformly accelerated observer who has his sort of closest point of closest approach to the origin will be at t equal to 0. I can always pick my time variable that way. And then I will have, of course, as time goes by, this observer is going to get closer and closer to speed of light. And they came in, I guess we would call it decelerating now in this direction here, right? So the word line looks something like this. In fact, it's straightforward to see that the parameterization of a word line of a uniformly accelerated observer is going to be given by something like this. And let's call t, lowercase t, this is now just going to be my affine parameter for the parameter that I use to describe this curve. And this is 1 over alpha hyperbolic sine alpha of t. Now you can see t will go from minus infinity to plus infinity, cosh on the other hand. So this point here is at x equal to 1 over alpha. Okay. Now we can calculate the magnitude of the forward velocity here. And that's just going to be the usual way. We're in a Minkowski background, so this is easy. And this is easily shown to be minus 1, right, as it should be. So that's... And then we can also calculate the proper acceleration squared, and we will find this is, of course, given by And not surprising, this is, of course, by alpha squared. So alpha is the magnitude of the acceleration. And this is the acceleration of that the observer will feel in their own rest frame. Okay? Now, what we'll do now is we will go to Euclidean signature, and we'll do it both for the parameter t, which we'll call I tau, but we will also do it in the Minkowski space. So t will go to IW, right? Then, easy to see that x will be 1 over alpha cosine alpha tau, right? T, or W, sorry, will be, so the hyperbolic variables just become trigonometric functions. And we see that the space-time diagram now, this is now W versus X. Instead of having this hyperbolic structure there, it's just a circle. Right? It's a circle of radius 1 over alpha. Okay? And obviously, we see here that tau has periodicity now, which is 2 pi over alpha. And so we infer from this that there is what's called the Unruh temperature is proportional to the acceleration is given by alpha over 2 pi. So you see this is very similar to the Hawking story with the acceleration playing the role of the surface gravity. Now, to go further, I'm going to go back to the Lorentzian signature, but I'm going to introduce a new coordinate. I'm going to introduce Rindler coordinates. So Rindler coordinates are yeah, okay. So I'm going to write my t as chi sinh alpha times t, right? X is going to be chi cosh and I'll leave alpha is just a parameter that I'm free to. So what this does for me is it will, if I again plot this here, here's t, here's x. So and I look at this wedge here, which is where the uniformly accelerated observer was moving before, and we'll see that this region here is, so this is the region covered by the chi, so the t chi coordinates. All right. And this is, so what I'm going to do now is I'm going to consider a massless scalar field. And actually, given that the motion is just in one direction, let me, for simplicity, just restrict to a two-dimensional Minkowski spacetime. So I'm going to take a massless scalar field in d equals 2 Minkowski spacetime. okay? And take my initial Cauchy surface to be at capital T equal to 0. Okay, so I'm going to take my Cauchy surface to be this, just the x-axis. And I'm going to divide it into two parts. There is the right part, and there is the left part. This is just x larger than 0, x less than 0, right? So so R is x greater than 0, L x less than 0. And now I'm going to think about sort of clearly, if I want to describe this scalar field, the state of this scalar field, it's not enough to have this coordinate system here, t and chi. I need a second one for the left part. So these are called. This is called the Rindler wedge here. This region that's covered by this part here. And so if I really want to describe the scalar field, I will also need a corresponding coordinate. If I insist on using Rindler-like coordinates, I will need two of these. And of course, this is ultimately where the Andrew effect is going to come from, because if I insist on then only using this right-hand wedge, then I will need to trace over degrees of freedom here on the left, and that's going to lead to a thermal density matrix over here. But let's see how that works in a little more detail. So what I'm going to do is I'm going to work with null coordinates on both sides, because I'm going to be interested in radiation that's going out either to the left or to the right, or coming in. So this is a massless field, so its waves are going to travel along in a null direction. So I can write, on the one hand, I can write this is, of course, just minus dt squared plus dx squared. And I can write this as I did yesterday for the part that was inside my massless shell. This I can write as dv du with capital V being t plus x, capital U being t minus x. Okay? But now I'm also going to but it's also not hard to see, if you use the Rindler coordinates, that you can write this as minus alpha squared chi squared dt squared plus d chi squared. So I just do that coordinate transformation, I work out what my line element is, and this is the answer I get. And this is going to be valid for chi greater than 0, so this is going to be describing this region here, but let's push on. And then I'm going to define chi as e to the alpha times rho. I mean, these should look rather familiar. I'm doing it exactly parallel coordinate transformations here as I was doing for the black hole space-time when I went to Kruskal coordinates. If I do this, I will see that this is equal to alpha squared e to the 2 rho, right? 2 alpha rho. And then I can write minus dt squared plus d rho squared. This is exactly what I need in order to get, to bring this into null form here as well. And I can write that as minus alpha squared e to the alpha times v minus u, lowercase dv du, with this time around lowercase v is in Rindler coordinates. t minus rho. So far, this is just manipulation of the metric. And now I can immediately read off the relation between these null coordinates. I see that v is e to the alpha times lowercase v, u is minus e to the minus alpha times lowercase u. And if we go back here, we see that the v and u, lowercase v and lowercase u, they basically will, as I move in this direction, null direction, my lowercase u is going from minus infinity to plus infinity here, right? So that, and the v goes from minus infinity to plus infinity, going that way. So we're covering this wedge here. But obviously the other variables, the capital V and capital U, they cover the whole thing. So they're analogous to the Kruskal coordinates we had in Schwarzschild. And these are, the Rindler coordinates are analogous to the Schwarzschild coordinates. Right? So in Rindler space, if we had started with the Rindler metric, we would have said, well, that looks like we have the metric is degenerate here, along here, but we would then realize that this is, of course, a coordinate singularity. We can switch to the Minkowski coordinates and cover the whole plane. So the analogy is quite strong here. And now I can start thinking about doing mode expansions. I'm doing this massless scalar field theory. So I'm going to do mode expansions in these different coordinate systems, and I'm going to compare, see. And what I'll be interested in is, of course, the Minkowski vacuum, which is something that it's the state that is annihilated by the annihilation operators associated with positive frequency modes in Minkowski time. I want to ask, what does that vacuum look like from the point of view of the Rindler coordinates? Because those are the coordinates I would use for a uniformly accelerated observer. All right, so that's the next thing I want to do. So we can do a mode expansion. In Minkowski coordinates. So we would say phi of capital X and T can be written as sum over my modes, UK, just as before. And my UK are the plane waves now just in one dimension. Right. And omega k here is just, as before, I'll define that to be positive, so it's for a given k. So if k is negative, this is a left mover. If it's positive, it's a right mover. In fact, let's just write that out here. They have k greater than 0. And then we're saying that UK is actually e to the minus I omega u. And then the left movers have k less than 0. And then uk, call these right movers, call these left movers. They have, well, let's just leave it at that. These are Minkowski modes. I'm not yet in the Rindler. Right? Okay. And the Minkowski vacuum is annihilated by these guys. And the sum, of course, extends over both left and right movers. So far so good. We're just doing massless scalar field in Minkowski space. But now let's think about this field equation in Rindler coordinates. So let's take the massless, so take the Klein-Gordon equation, massless Klein-Gordon equation, and let's transform to Rindler coordinates. Now, we can work through the transformation, or we can be clever, and we know that this is a conformal theory. Massless scalar field in 2 dimensions is a conformal theory. So we know that the scalar field equation in Rindler coordinates is going to have exactly the same form. So, but you can check this by just doing the transformation. Is going to be it's the same form as it would have had in the original x and t coordinates because of the conformal symmetry. And now I can also write down mode solutions. And if I'm in the right wedge, I'll call these UK R. They are going to be e to the I minus I. I'm just repeating what I did before. K rho, right? And omega k is as before. So I can have modes with respect to the Rindler coordinates, which are going, you would call them left and right moving here. But of course, if I map them back, they are moving either sort of towards the origin or outwards, right? Because rho is a radial coordinate. And then I can also have on the left and there is sort of a convention that I'm going to follow here, which is that you actually put a plus here. The same omega, of course. And the sign convention is that if you think about it, a right mover on the left here, on the right here, moves away from the, whereas a right mover here on the left is actually moving towards, so they're going inwards. And that's why we can sort of keep track of that by having this sign here. You can also kind of, another way to interpret it is that you say your Rindler time moves upwards over here, and it's natural to think of it going in the opposite direction in the left wedge. That's how it works for a Schwarzschild black hole. So anyway, we're going to follow this convention. And now we can think about taking our scalar field on this Cauchy surface. We'll need both the left and the right Rindler modes, but those should suffice because they cover now the full. So we would write that. So we would write our phi now as a sum over k. And now I'll need a little bit more notation. I will write this as b left k, u left k, plus b left k dagger complex conjugate, and then I will have a b right k and a b right k dagger, like so. And that should, where I write explicitly that I need actually two sets of Rindler modes to describe the full field. All right. So now let's think about a right-moving mode that's here on the right. So, and ask, how do we describe that? Well, it's only defined in the right wedge, which means that, so if I have a right-moving Rindler mode in R, so that is this guy, UKR. It's going to be a function of my lowercase u that I defined. Maybe I just erased it now. And it's basically going to have support on the right, so it's 1 over and it's going to be 0. Okay. And I can also write it now as, in terms of the Minkowski coordinates, so I can undo that transformation that I had before. And then I will have e to the I omega k over alpha log of minus u. This should look familiar from yesterday. This is very much similar. And of course 0 otherwise. This is if u is less than 0 and 0 if u is greater than 0. Because that's okay. Now, and this is of course not a positive frequency mode when it comes to, if you think about it in terms of the UV, capital UV coordinates, or the original Minkowski coordinates. That should be pretty clear. Yes. Yes. Yep. Absolutely. That's exactly. And so we can really repeat the story from yesterday. So this guy is now So if we insist that we are in a Minkowski vacuum, right? And if this guy is actually not purely positive frequency there, but actually has some negative frequency component, well, then that's going to lead to, then it's going to actually, when we look at the corresponding mode coefficients, it'll tell us that from the point of view of the Rindler vacuum, this guy actually has some particle excitation. So we can actually, we can do the overlap integral, we can calculate the Bogoliubov coefficient. It's basically the same integral as we did yesterday, and we'll get, of course, then the same answer. But I'm actually not going to do it that way. I'm going to show you another way, which is how Unruh actually did this originally. So we can repeat the calculation of the Bogoliubov coefficient. And we would end up saying that if I'm in the Minkowski vacuum and I calculate A right dagger K, AK right, I would find that it's actually going to be proportional to 1 over e to the 2 pi omega over alpha minus 1. Right, that was our answer yesterday. But so let's not do it that way. Let's actually do it in a different way. At least I'll sketch how to do it in a different way. And so what Unruh did was to say, okay, let's ask ourselves, so this guy clearly, there's something missing for it to be a positive frequency mode. Let's figure out what's missing and let's add that in. And then we will have a positive frequency mode that annihilates this vacuum. But of course, what we'll find out is that what we have to add in is actually a negative frequency mode in the other wedge on the left. So let's see how that works. All right. So this is we construct a positive frequency Minkowski mode in a way that agrees with UR K of U for U less than 0. And I'll call this guy SK, just to call it something. And it turns out what you need to do is the following. So you do have your 1 over 4 pi omega k. Then we said we had an e to the I omega over alpha log minus u if u is less than 0. And then what you need for the positive 4 pi omega k, it actually turns out to be e to the minus pi omega over alpha times e to the I log u if u is greater than 0. So now to see this, and I'm not going to do it in all detail, but we can talk about it in the discussion session later on today, if you like. You let Z be So you write this. This is basically just the polar coordinate rendition of the z here. You let it be, okay? And so that u less than 0 corresponds to phi equal to pi. U greater than 0 corresponds to phi equal to 0, right? So I'm basically taking and looking at a complex variable that is, has u as the, agrees with u on the axis, on the real axis, right? Now, and I chose this sign here, or Unruh did, because what he wants in the end, he wants to construct, what you want to show is that this mode here, then this mode, which is sk of z now, omega k, you write it everywhere as this. Log of z. Okay? Now this is a mode that is actually, by construction, it is analytic everywhere in the lower half set. And this I'm not going to show here, but we can, it's not hard to show. And then what that means is that then we can ask, so for it to be a positive frequency mode, it means it's not allowed to have overlap with any negative frequency mode, right? So what you need to show is that the integral minus infinity to infinity du of sk of u e to the I omega prime u, where omega prime now is, and this is going to be equal to 0 if omega prime is less than 0. Okay. And that's because this guy is analytic in the lower half plane. You can do, you're doing your contour integral. You close the contour down this way, and there's no singularity here. You're going to get 0. And so this is a positive frequency mode then in the u coordinates. And we can now go back and ask, what do we actually get? Well, you put in positive value of you let z be on the positive u axis. Then this, of course, is going to be, then you simply get this part, which is on the left wedge, right? You let u be on the negative axis. You're going to pick up a minus I phi from the angle here. That combines with the I omega over alpha here to cancel this piece, and so then you get this. So this is exactly the mode that you want, and because it's analytic in the lower half plane, you're guaranteed that it is a positive frequency mode. And then, of course, what we look at here, this is just a constant, but this is actually a negative frequency mode on the right-hand side, on the left, right? So we have gotten ourselves so the u greater than 0 part of this guy it can be interpreted as a negative frequency Rindler mode in L, okay? Basically, you let u be greater than 0, then your e to the I omega over alpha log u is going to be an e to the I omega u. Now you have to think about how do you actually go to Rindler coordinates on the left wedge. When I'm on the left wedge, capital U is positive, is actually negative, right? They both switch signs. So I have to do a slightly different coordinate transformation. So here, actually, U is e to the alpha U. This is the U now on the left. And V is minus e to the minus alpha V. Okay. So basically, the global coordinate, globally defined coordinates is capital U and capital V. But when V is negative, I have to then sort of, the Rindler coordinates have to be adapted to this. Okay. So we do that. And then what this means then is we can write that Sk of U is actually a UKR, and that, of course, I have to go back to the e to the minus pi omega over alpha. So let me just write it like this. So we construct, by construction, it was equal to a right moving mode on the right wedge. And then on the left wedge, we have a negative frequency mode. Okay. Now, the Minkowski mode, since this is a positive frequency mode with respect to the capital U, it tells you that the Minkowski vacuum should be annihilated by the corresponding mode coefficient, right? Mode operator. Right? So let's see what that gives us. Basically, I can write this then, that my B R K minus e to the minus pi omega over alpha B left K dagger. This should annihilate this vacuum, right? Now, these are formal expressions that I have here because I have to be a little bit, strictly speaking, of course, these guys here, they act on the Fock space that's built on top of the Rindler vacuum. This is, of course, a state in a different Hilbert space, but let's put that aside for the time being. We're simply sort of, let's just view this as like it is what it is, which is a formal argument. So what this says, it says that when I apply a Rindler annihilation operator to the vacuum, I get right? And let's call this equation 1. Now, similarly, I can start with a Rindler mode on the left. We can start with a Rindler mode in L, go through the same steps, we're going to find that that, when applied to this guy, to the Minkowski vacuum, is also going to be like the, now, the way to think about this is you can, this is really, if you want to solve these equations, you can really just kind of do that by inspection, because this is an equation that tells you that this guy should be an eigenstate of the annihilation operator with, which is, if you think about this as sort of formally as its eigenvalue, it's going to be a form of a coherent state. And it has to be a coherent state with respect to both sides, left and right. So the answer you get they're solved by the following expression. Again, it's a formal solution. The Minkowski vacuum has some normalization factor. It's a linear equation, so I won't be able to tell you the normalization from this alone. Then you have to take a product over all possible k. You have the exponential of e to the minus pi omega k over alpha, right? And then you have the b left k dagger, b right k dagger, acting on the vacua of the. So these are the Rindler vacua on the right and the left. Okay. If you simply construct this and then you apply this operator, you will find you bring down exactly this. So this is, and this works for all values of k. Okay. So what you're seeing here is that the Minkowski vacuum is, formally at least, is an entangled state between the left and the right. So it's made of correlated pairs of left and right Rindler excitations. Okay. So, but now that we have it in this form, we can ask, what if we're only going to look at observables on the right wedge? Well, then we would perform a trace over the left variables, and that's easy enough now. Now we can simply do a trace over the left wedge with this. Yes? Yeah. Oh, yeah, absolutely. Well, it's good that somebody is awake. Sorry about that. Yeah, no, that should have been B. Caught it just in time. All right, so now we have a formal expression for this thing. We can construct a density matrix. We have a, so the corresponding density matrix is, let's call it, so that's given by, right? And then you would plug in this expression, and then you can carry out a trace. Over the L modes, actually gives a thermal density matrix for the R modes. What you will actually find is that this, it's conventional to write the normalization factor with that you get here is, you will get a sum over M e to the minus 2 pi alpha, sorry, omega m over alpha. And these are now going to be where this is actually now is a basis of all Fock states built from the Rindler vacuum, right? And you get a factor of 2 here because when you do this, when you calculate this guy, you get two exponential factors here, and you see that this is exactly the en route temperature that we get here. So we're reproducing what I said before. If we had done this Bogoliubov coefficient, and we can actually now we can normalize. We know that this z here has to be basically the partition function, right? E to the minus 2 pi omega m over alpha. And this is just so that trace rho r is equal to 1. Right. Now, of course, if you're really doing a quantum field theory, there are issues here that I'm completely glossing over, like this is a divergent expression, so you need to regularize, and there is a longer story here, but the basic statement that you get a thermal density matrix that does hold. Okay, but so this is this whole argument that I'm making here is it is a formal argument, and there are certainly details to be filled in and issues to be resolved. And I don't want to give the impression otherwise. Yes. Tell you what, the next thing that says here in my notebook says there is a corresponding construction for an eternal black hole. So let us do that. Okay. So the answer is emphatically yes. In fact, that is how Unruh did the calculation. No, so indeed, there is a corresponding construction for an eternal black hole. And so remember there, the Penrose diagram looked something like this. So again, I can think about this. So this would be my right, my left, okay? And basically for this correspondence, alpha goes to the C, UK, R goes to the Schwarzschild type modes in region 1. This is region 1 here of the, and then we call this region 2, right? This was region 3, this is region 4. And then my U left, okay, is going to go to Schwarzschild mode in 3. Okay, so and the capital U, of course, was, as I said earlier, those capital U and V are the Kruskal coordinates. So, and then the vacuum that plays the role of the Minkowski vacuum is this so-called Hartle-Hawking vacuum. That is the vacuum which is annihilated by the positive frequency modes with respect to the Kruskal time when I've gone through that procedure. And then you will see that that vacuum is actually, it's an entangled state of Schwarzschild modes on the right and modes on the left. You can do a trace over over the degrees of freedom over here, and that gives you a thermal density matrix for modes on the right, okay, in exactly the same fashion. So I'm not going to repeat that. Okay. So we've seen that a black hole formed by gravitational collapse, asymptotically flat spacetime, that gives rise to, it emits thermal radiation at the Hawking temperature. Now we've also seen in this lecture that a uniformly accelerated observer will detect thermal radiation at a temperature that's proportional to the acceleration. And these two effects are intimately related. As you've seen, the mathematics is practically the same. But there's also, and it's not just the mathematics, the physics of acceleration is, of course, to the equivalence principle is very much also the physics of, the physics of gravity is the physics of acceleration. And so what I'll do now in the second lecture, let's take a break now for a few minutes, but in the second lecture I want to sort of elaborate on this connection between the Hawking effect and the Unruh effect, and also kind of sharpen the notion of what do we mean by an observer detects certain, radiation of certain temperature. So I'm going to go through the construction of what's called the Unruh-DeWitt detector, and but let's take a break before we go there. Okay, now it's on. Okay, let's let's get started again. This was a slightly longer break than intended because I guess there were questions, things I didn't make clear before. So I may actually steal some of your time. There's just in the interest of getting through the material that I wanted to cover. So we may go for maybe more like 40 minutes rather than a half hour now. Hope that's okay. So now we're going to talk about how do you actually detect this radiation that we're talking about. And there's a clever construction from Unruh and DeWitt. So we're again, think about a scalar field. And let's now put it in a black hole background. It can actually be also in just Minkowski space. If we want to talk about the Unruh effect, we would put it in Minkowski space and think about accelerated observers. And then this kind of detector is simply a quantum mechanical system that's coupled linearly to this field. And this can be any quantum mechanical system, can be a two-level system or a harmonic oscillator. It doesn't really matter. For the argument, we'll see that in a minute. And we're carrying this along. The observer has this detector, which is this quantum mechanical system, and it's carried along the trajectory of the observer. Okay, so the trajectory we're going to describe as just a parameterized curve in the background spacetime, and tau here is the proper time of the observer. Okay, so this is really just the word line description of the observer, and we're going to couple. It's carried along and it's coupled linearly to the field. So basically, there will be some interaction. So the quantum mechanical system will have its own Hamiltonian, but then there will be an interaction piece, which will have some coupling constant. And then there are a few things that will come into it here. I'll write it as a product of okay. So what are these things that I have in that formula? So C is a coupling constant. By the way, is this thing on? Okay, good. Now, this chi of tau is is called the switching function. So basically, and it has compact support, let's say. So basically, here's our function chi, and it just looks like something like this. So basically, there is some time, proper time tau, 0, when we turn on the detector, and then we turn it off at tau 1. Right? So we want to build that into the formalism. And this is going to be important if we want to think about this trajectory as actually, let's say you have an observer who's in free fall and is moving towards the black hole, then this background is going to be changing. You would expect perhaps the temperature that this, we're going to see that this will register a temperature in a certain sense. And then you would expect that temperature might change. I mean, the environment is changing. So you want to be able to do a measurement. You want to be able to say that I am measuring this at some given time. So that way you control that. This is something that the observer can control, basically. Now, this mu of tau is called, it's basically, let's call it a monopole moment operator. So it's coupling to the field itself directly, so that's why we call it a monopole. You can imagine other ways of coupling. You could have a derivative coupling here, and actually in two-dimensional systems you probably would prefer a derivatively coupled detector, but and this operator acts on internal states of the detector. So basically we have, if you think about it, we're doing time-dependent perturbation theory on some, quantum mechanical system like you did in your first quantum mechanics class. And this mu here is just some interaction Hamiltonian, some piece. Let's say that our system is a two-level system. It might be an off-diagonal matrix that will couple the two states. So it could be as simple as that. All right. And now let's just do a little bit of formal. So let H be the Hamiltonian of our system. With just some energy eigenstates. Let's call them EI. So that H acting on EI is just given by some energy. Okay? And let's write we have the following expression. We call mu ij is simply the matrix element of our monopole operator here, the transition, the interaction here, and let's take it. So these are just numbers. They are matrix elements of this operator evaluated at time 0. Okay. And now let's assume the system starts in a simple state where the field is in its ground state, and then we're in some initial state. Okay, so this is what describes the detector state, and this here is the field state. And we're going to assume the start with the field in the vacuum, and then we doesn't really have to be the vacuum, but let's say. And now we're going to formally calculate the transition amplitude to some other state. Okay. Let's call it EJ tensor beta, where this is now, can be any field state, right? So we're going to go from a particular initial state to a particular final state for the detector, but we're actually not going to keep track of what the field is doing. It's allowed to do whatever it wants. Okay? So this transition amplitude is given by, well, there's going to be a C. We're going to have a minus infinity to tau. And then we simply put in here, we have our chi of tau, we have our mu of tau, the operator, we have our field operator, and then we have the state we started from, right? And this guy I can write as e to the IH tau mu of 0, right? E to the minus IH tau. And since these are energy eigenstates, I can commute them through, and so I'll pick up just my matrix elements, mu ij, yes? Say again. That should be ej, yes, thank you. Okay? So we can actually say that this is equal to C times mu ij minus infinity d tau, chi of tau, e to the I ej minus ei, right? Tau, sorry. And I will have beta phi of x of tau, right? Yes? Let's say it's the vacuum of the theory, yes. It can be, if you prefer, yeah, sure. It's just some state. Okay. Yeah, let's say it's the vacuum state, and then we want to actually calculate what is the probability that it makes a transition to an excited state. Okay. Let's say it's a two-level system. We start with it in the vacuum state, in the lower state, and then we ask, what is the probability that we'll actually gone up to the upper state? And then if we measure that, we would say then our little thermometer has clicked. Okay, we'll say that if it makes a transition, then the detector has made a detection, right? So let's ask, what is the probability to find ourselves to make this transition? Well, it should be the square of the amplitude, right? So we calculate it's P, EI goes to EJ, should then be C squared. Let's assume that we have a real valued coupling constant, C squared mu ij squared, right? Now I'll have to do two time integrals, infinity d tau prime. I will have a chi of tau prime. I will then have e to the minus I e j minus ei tau minus tau prime, right? Times. Well, there's going to be a sum over all beta phi of x of tau beta tau prime, right? Because I'm only interested in, I want the total probability to making this transition. Well, then I have to sum over the probabilities of making that transition and whatever transition the scalar field does, right? And then I can use that sum over beta is, of course, is the unit operator. So this tells me that this P, I goes to J, is then equal to, now if we look at what is this, if I do this sum and I use that what this really is then is just what you can call G tau tau prime. It is the pullback of the Weidmann function of the field to the word line, right? Right. So this is the pullback of field to the detector. And if we make this a simple system so that these matrix elements are easy to compute, then really the physics is all sitting in this Weidmann function of the field. Right. That's what is giving us the probability. And now, so I can really write this as the following. I goes to J is C squared mu ij all squared. And then there is some function which is only a function of the energy difference in the, let's call that delta E. Okay, with so this f of delta E is going to be integral to infinity d tau chi of tau I'll write S as tau prime minus tau, so I can change the variables in the tau prime integral to S. And then I will have e to the S, I will have here e to the I delta E times S key of tau plus S g of tau plus s, right? Where that's the Whiteman function, or the pull by. And the point is that this here is independent of the details of the detector. It involves the switching function and the correlation function of the field. Okay, so we've separated out the... and now let's look at a special case, which is the case that Unruh was looking at. So we take the special case. We have a static detector. So it's a fiducial observer who just sits there somewhere in the, or maintains their position in the background. So it's a static detector that's always on. So that means that chi of tau is simply equal to 1. And that also tells us that g of tau prime is actually just going to be, because we're in a static black hole background, let's say, our observer is not moving. So basically, time translation symmetry tells that this is going to be the case. All right. So in this case, you will see that this first integral here just factors out and gives us infinity. So that doesn't look good, or does it? Well, maybe we shouldn't be surprised if we're having a detector that's on forever, that it, of course it's going to make a transition eventually. So what we're really interested in is the time derivative. What is the probability of making a transition per unit time? So let's calculate that then. Well, we can read that off from here. Yes? Well, this is what you get. Yeah. No, we just, and we just, so there's no time ordering involved here. Well, but this is simply what you get. Okay. And so let's consider then the transition probability per unit proper time. Is then going to be c squared. Well, the matrix element is, of course, sitting there. Then we need df du, or df d tau, sorry. So we can just strip, basically what this does, it strips off this first integral here. And this is, but for this to work, of course, we have to assume that we've had the detector is always on, and we're simply calculating the transition rate. And so that is going to be given by this expression here, ds. Okay. But now, so we said this is an observer who's not moving. So it's a fiducial observer at some fixed value of, and then, of course, things simplify. And I'm not going to go into the details here, but basically, what Unruh did was to show that a fiducial observer would actually see a transition rate that is the same as if the detector was in a thermal state at a temperature which was the local, was the Hawking temperature divided by the square root of. So that is what was Unruh's. And we can kind of motivate that here, because so the fiducial observer has basically R of tau is equal to R, which is a constant. It's theta and phi are also constant, and the only thing that's progressing for that observer is, of course, its time. Okay? And then let's recall that the Euclidean geometry, black hole geometry, let's say if we're doing a Schwarzschild black hole, it looks something like this, right? We have R, there is the RH, and then we had this kind of cigar-like structure, right? And it has a period in, so there's an angular variable here. So this is R equals to RH here, and there is a period here. It's periodic in Euclidean time. Okay? And this tells you that when you solve for your green function, you just solve the field equation on this background. This green function will inherit that periodicity. So you will find that g of s is equal to g of s plus I beta times square root f of r. That's going to be, so basically we're sitting at a constant value of r, and the Euclidean time is evolving in a circle here with a local radius, which is given by this period, sorry. Okay? And so for this observer, it's clear that we should be evaluating a thermal green function. And therefore, we conclude that the detector is going to, this transition rate is actually going to be it's going to have a thermal character because of this. All right. Now, everything we said could have been done not for a fiducial observer in a black hole spacetime. We could have had a uniformly accelerated observer in a Minkowski spacetime. Their uniform acceleration, as we saw at the beginning of the lecture this morning, we saw that corresponds to going in a circle whose radius is governed by the acceleration. And so that is also going to give us a periodicity in the green function. And therefore, that observer is also going to see a thermal radiation. But a more interesting, or another question, this is of course, maybe not a more interesting question, but a different question is, what would an observer in free fall see? Well, the formalism here, before I made that special case, should apply, right? But the problem with the infalling observer is that their word line, even if it's just simple radial infall, the word line is more complicated, and actually calculating this green function is tricky. Usually it's done in this case using some clever arguments, some contour deformations and so on. And it's crucial that everything is only a function of time here and not of space. So it is more complicated to answer the question for an infalling observer, but it's an interesting question, because what you will notice here is, of course, that this temperature is blowing up when we get in here. Now, Unruh told us that an infalling observer should not see that. they are more or less, they are, well, that is what your expectation is from the equivalence principle. You're moving in if it's a large black hole, you go through the horizon where it's not so strong curvature. You may see something, but you should certainly not see a divergent flux of thermal radiation. But it's kind of tricky to complete this computation. So what I want to show you is an alternative method which allows me to conclude something about what an infalling observer will see, and especially interesting to do that not just for a Schwarzschild black hole, but also for a ADS Schwarzschild black hole, where the Hawking temperature can be very large, and so it's a reasonable thing to ask, what does an observer in free fall see there? Okay, so that'll be the topic of the first half of this afternoon's lecture. We can start setting it up a little bit. So let me do that just in the interest of. So I'm going to use, and actually, sort of as a byproduct of this, we're going to see it's kind of an interesting, at least I find it interesting, that you can really think of the Hawking effect in a d-dimensional black hole background. There is a very precise sense in which it is actually the Unruh effect in a higher dimensional geometry that is flat. And so this is some formalism that was developed by Stanley Deser, and I think Deser and Levin wrote kind of the papers on, and they showed that for a fiducial observer, you can use this, they call it the global embedding into Minkowski spacetime, so the GEMS method, and they applied it for various types of fiducial observers for various different black holes, and every time they would find that if they used this embedding construction, and so you basically take, let's say you take Schwarzschild black hole in 4 dimensions, there is a 6-dimensional flat space Minkowski geometry that you can embed it into. This embedding was worked out by Fronsdal in the 50s, late 50s, and was kind of a part of the discussion whether this Schwarzschild sync, this predates Kruskal and Zakaras. And so what Fronsdal was basically trying to establish was whether you actually could, whether it had meaning to go through this event horizon of what we now call the event horizon of the black hole. And so there's this higher dimensional, and it's a global embedding. You can embed and smoothly embed this black hole geometry into this. This is basically, there's a statement in Riemannian geometry which says that any Riemannian manifold can be embedded in a sufficiently high dimension flat manifold. And we're extending that here to pseudo-Riemannian to do it for space-time manifolds. And when you do this, you can ask, what is the word line, if you follow the embedding, what is the word line of this fiducial observer? Well, you will not be all that surprised to learn that that is actually a uniformly accelerated observer in the higher dimensional spacetime, whose acceleration is precisely such that the Unruh temperature associated with that accelerated motion is exactly the local Hawking temperature of that the fiducial observer sees. You can do this, like I said, they went through a whole, basically you took the list of all the static black hole solutions we know, and yet this worked every time. And then what Brynjolfsson and I did back in some while ago, we followed up on this by saying, well, we can actually try to think of this also for infalling observers. Now you need to do a few things there. There's some physics you need to kind of argue for. First of all, you have to accept that there should be something called an instantaneous Unruh effect. That is, if you have, so all of the computations I did here, they all assumed that you had these accelerated observers, they were accelerating forever. And it's very much here, when you factor out things here to get the transition probability, you explicitly use the fact that it was not changing with time. However, most physicists in this business would think it's an interesting question. Can we see the Unruh effect in the laboratory? And there are some analog black hole systems or analog gravity systems where people are actually trying to do that. But once you ask that question, you're obviously thinking that this is really a physical effect. That is, if you have an accelerated observer who was not accelerating a month ago and will not be accelerating 3 years from now, you would still expect to see radiation from them, right? So that you have to, you're assuming that there is a meaning to basically your thermometer here, your Unruh DeWitt detector. If you switch it on for a little while, you would expect to see transitions even though the thing is not on for. But in order for this to be an interesting setup, then you need some separation of scales. What you need is, so if you want to think about, what does so instead, if you have an observer in free fall, then it's not static, right? And so you would need to solve for this green function along the trajectory, and you would ask that there be a separation of scales. So you need to solve for, if we're going to be working in this along trajectory, and you need separation of scales which is, and a separation of time scales really. And this is going to be the same kind of consideration that you need also for the embedding story that I'm going to tell you in the afternoon lecture. You need this. This is the time scale, typical time scale for detector transitions, right? We're doing quantum mechanics. So this is for detector transitions. So this is going to be, if it's thinking in terms of quantum mechanics, this is atomic physics scale or something like that. So it's quite short. And then, of course, you want to have your delta tau x, which is this is the switching time. So basically, this is something that the experimenter can control. They can turn off on their detector, and in order for this to be a meaningful thing, it better have it turned on long enough for there to be, for the detector to be able to respond. So you need this to hold, right? And then for this to be a meaningful measurement of a temperature, then of course, this has to be, so this last one is the time scale of change in the detector environment. And so, roughly speaking, you would expect this guy to be something of the order of a Schwarzschild. So if you are near the horizon falling into a black hole, you'd better be able to do your measurements on a time scale that's short compared to, because if your detector is on for much longer than this, you're doing some sort of averaging over temperatures in a range. Okay. Now, actually doing this for the Unruh detector in this formalism that I was showing you, that is not a problem. In fact, there's been some progress over the years, but I believe this is still an unsolved problem. So that's not a good way to do it. So what I'm going to do is to describe for you this indirect way to doing it, where we embed into a higher dimensional geometry and basically identify the acceleration that we see locally in the higher dimensional geometry, we're going to call that the local en route temperature there, and we're going to interpret that as the. So there are some details that go into it that I will show you this afternoon, but let's stop here. Right.